On December 11th, NASA issued a statement suggesting that 3 at last may be seeding life right here on Earth. This object is constantly shedding fragments, spreading dust rich in organic compounds like seeds of life into the star systems it passes through. At last carries an anomalous CO2-H2O ratio, its icy shell having been recycled by radiation over billions of years, potentially forming magnetic minerals that shield and protect the organic material inside. Observations show that Atlas maintains a steady brightness, like a world slowly waking up with a teardrop-shaped structure pointing toward the sun, strange polarization signals, a smooth, non-gravitational acceleration, and even brief infrared thermal pulses that resemble the activity of a mysterious engine. It has also vanished once then reappeared at a new position, accompanied by a stream of data that looks like future rendezvous coordinates. Taken together, these details fuel the hypothesis that Atlas may be a swarm of many small fragments moving in tight coordination, or even a structure capable of actively controlling its own trajectory. Yet even before this new study, scientists were already unsettled by a deeper question. What kind of life-bearing seeds is 3i Atlas actually scattering across the universe, and is Earth now directly in their path? We'll dive into that research next. NASA is already watching the fragments of 3 Atlas fall. On deep space monitors, tiny shards and dust clouds peeling away from 3 Atlas show up as faint drifting signatures, some of them on trajectories that will cross Earth's orbit within years. In simulation rooms, engineers run scenario after scenario, asking whether any existing defense system can truly steer those pieces of 3i Atlas away from our planet's thin shell of air. They test kinetic impactors aimed at larger chunks, hoping a hard nudge could make the biggest fragments of 3 Atlas miss the narrow corridor that leads toward Earth. They model laser ablation on smaller pieces of Atlas, trying to see if gentle vaporization could slowly shift their paths. Every time the same problem returns, even if the largest fragments from 3i Atlas can be deflected, the finest dust and micrograins from Atlas remain almost impossible to herd. On paper, the official line says the risk from 3i Atlas is low and under control. Inside the labs, the language is more careful. Teams admit that they can shape probabilities, not guarantee outcomes, and that some residue from 3i Atlas may still slip through any net they cast. 3i Atlas resembles a living planet seed slowly moving between the stars. If Bennu shocked us by carrying amino acids and the precursors of life, then 3. I-Atlas looks like the push-to-the-limit version of that idea, an older, darker, more heavily equipped Bennu born to wander across the galaxy. 3i Atlas is not only carrying chemicals, Atlas is scattering them. Every time 3i Atlas is warmed as it approaches a star, tiny fragments, dust grains, and minute ice particles peel off the surface of Atlas and escape into the surrounding space. Each grain that comes from Atlas can contain complex organic compounds, magnetized minerals and molecules that have been tempered by radiation, like ultra-small capsules designed to survive when passing through the atmospheres of distant worlds. If that really is the nature of 3 Atlas, then Atlas is quietly seeding every stellar system it passes through. Some fragments from 3 Atlas will fall into gas giant planets, some will drift off into empty space, but there will always be grains that collide with rocky planets, spiral down through their atmospheres, and dissolve into oceans, lakes, or underground water reservoirs. The serious question is what happens if that process occurs with Earth. Forecasts have already shown that after its closest approach, Earth will pass through the region of space that has just been disturbed by 3 Atlas sweeping through the dust and tiny fragments left behind by Atlas. If only a very small portion of that material from 3 Atlas reaches the upper atmosphere and survives the fall, then we are no longer just observers of Atlas. We are directly allowing the chemistry of 3i Atlas to merge into the thin, fragile layer where life on Earth exists. Here is where 3i Atlas behaves differently. Observers saw Atlas maintain the new brightness level night after night, even as the 16-hour rotation carried every longitude into view. If only one small patch had activated the light curve of Atlas, would have pulsed, brightening and dimming with each turn like a lighthouse. Instead, the glow of 3 Atlas remained remarkably stable, suggesting that a large fraction of the surface was now involved. That stability leads to a striking hypothesis. Rather than a few isolated jets, Atlas may have entered a regime of widespread cryovolcanism, with volatile-rich terrain awakening all across the crust. Under this picture, sunlight penetrates the darkened rind of 3i Atlas, just enough to warm buried ices. Pockets of carbon dioxide, water, and other volatiles begin to sublimate in many places at once, feeding a more global coma. For scientists tracing the light curve, Atlas starts to look less like a sleepy snowball and more like a world stirring from hibernation. 3 Atlas becomes a slow cold analogue of a geologically active body trading lava for vapour, but still reshaping the thin layer between vacuum and interior. The idea is speculative, yet the data keep gently tugging in the same direction, away from a single accident and toward a coordinated change. In a calm way, that shift changes the emotional tone of the story. Atlas is no longer just passing through. 3 at last is responding to our star entering a new state after eons of darkness. The next questions lead us deeper inside at last toward the chemistry that those newly awakened gases reveal, and the magnetic minerals they may help create. Among the numbers that describe 3, at last 1 ratio stands out like a quiet alarm. For every measure of water vapour in the coma of Atlas, there appear to be roughly 8 measures of carbon dioxide. Spectroscopists are used to comets where water dominates, and carbon dioxide plays a smaller supporting role. In most solar system comets, that balance tilts the other way, and the pattern is familiar enough to feel almost comforting. With 3 at last, the measured CO2 to H2O ratio sits several standard deviations away from that norm, far out in the tail of the distribution. On paper, the anomaly is just a number. In reality, the chemistry of 3 Atlas whispers of a very different history of ice. Such an excess of carbon dioxide suggests that the outer layers of Atlas have been profoundly reworked by time, radiation, and emptiness. One possible story is that cosmic rays have spent billions of years breaking and remaking molecules in the skin of 3 Atlas. Simple ices on Atlas are split apart, recombined, and gradually driven toward more oxidized, carbon-rich compounds that are harder to remove. Over eons, water may be preferentially lost, while carbon dioxide remains trapped in a dark, compacted shell. Closer to the Sun, around that same 2.5 astronomical unit, mark the interior of 3 Atlas may briefly host tiny pockets of liquid water. In those fleeting zones where pressure and temperature allow metal grains mixed into the ice of Atlas can begin to corrode and transform. Iron and nickel inside 3I Atlas are slowly rearranged into magnetite, a mineral that naturally aligns with magnetic fields and can generate its own subtle signatures. If enough magnetite forms in the crust, 3I Atlas could carry a faint localized magnetic environment around its core. Such a field would gently shield the innermost organics on Atlas from the harshest charged particles, like a thin cloak wrapped around ancient cargo. The thought that a wandering body might build its own magnetic shelter through chemistry alone adds a quiet wonder to the portrait of 3I Atlas. In this view, the strange CO2 ratio is not an isolated oddity, but part of a larger pattern. 3I Atlas begins to resemble a carefully layered archive of ice carbon and magnetized rock-preserving material that might otherwise be stripped away. The next step is to ask what kinds of molecules that archive of Atlas may be protecting, and whether those ingredients resemble the building blocks of life. By this point in the story, 3I Atlas is no longer just an icy traveller in our minds. Atlas has become a layered object stitched together from ancient radiation-processed ices and slowly magnetized rock. When scientists compare the chemistry of Atlas with samples from meteorites and asteroids like Bennu, another pattern emerges. Those smaller bodies already carry amino acids, simple sugars, and pieces of genetic bases suggesting that the recipe for life's ingredients is common. 3 Atlas, with its extreme carbon dioxide content and long interstellar history, looks like a larger, older cousin that has had even more time to cook. In that calm hypothesis, Atlas is not a finished organism, but a cargo ship for molecules. The crust of 3 Atlas protects fragile chains of carbon like padding in a crate, while the possible magnetic cloak shields them from the sharpest radiation. Whenever Atlas passes near a star, gentle heating can lift a thin mist of gas and dust, releasing a small fraction of that chemical cargo into surrounding space. The anomaly is not that chemistry like this exists, but that 3 Atlas may concentrate so much of it in one wandering structure. Instead of random grains floating separately, Atlas bundles together ices, organics, and minerals in a single vehicle that crosses from one stellar neighbourhood to another. If a world with oceans or a thick atmosphere happens to intersect the dust trail of 3 Atlas, some of that material could settle into new environments. Thinking about Atlas this way softens the object's image. 3 Atlas stops feeling like a threat and starts to resemble a quiet courier moving building blocks rather than finished blueprints. Even if life begins independently on each world, a visitor like Atlas could sprinkle extra ingredients into the mix, nudging chemistry in directions we are only starting to test in laboratories. There is comfort in that idea, a sense that 3 Atlas participates in a slow exchange of matter between otherwise isolated systems. Yet the picture is still incomplete, and Atlas has more to show. As 3 Atlas moves closer to the Sun and into the gaze of powerful telescopes, shapes will appear around the nucleus that challenge this gentle, simple view and lead us into the next chapter of the story. On a calm night at the end of November, astronomers pointed Hubble toward a small receding visitor and saw a shape that should not exist. On the screen, 3 Atlas appeared not as a simple point with a trailing fan, but as the heart of a long, narrow teardrop, reaching straight toward the Sun. When the team measured the feature, they found that the sunward structure extended roughly 60,000 kilometers from the position of 3 Atlas. For comparison, that is several times the diameter of Earth, drawn out in a pale, almost symmetrical line anchored on Atlas. Under ordinary circumstances, comets grow tails that flow away from the Sun. Solar radiation pressure pushes dust and gas outward, and the motion of the nucleus through the solar wind sculpts long streamers that always lean anti-sunward no matter where the comet travels. By that logic, 3 Atlas should have worn its brightest features behind the nucleus, not in front of it. The data from Hubble quietly refused to follow that script. Images taken on November 30th show 3 Atlas, with a distinct enhancement on the side facing the Sun, a brightened wedge that tapers like a drop of liquid falling upward. Analyzed profiles reveal that the brightness along this sunward extension declines smoothly with distance, as if material is concentrated and confined rather than simply blown away. For the scientists involved, the anomaly is not just aesthetic. If the material around 3 Atlas obeyed the familiar balance of gravity, gas drag and radiation pressure, a 60,000 kilometer feature pointing inward should quickly smear out or reverse direction. Instead, the structure linked to Atlas holds its general shape at least over the span of the Hubble observations, as though some organizing influence is at work. That realization places 3 Atlas in gentle tension with textbook diagrams of comet tails. Either the environment around Atlas is stranger than expected, or the material near the nucleus of Atlas is responding to forces that are not yet fully captured in simple models. Neither possibility needs drama, but both invite careful attention. In the quiet of the control room, the strange geometry of 3 Atlas produces a different kind of emotion. The sunward teardrop feels like a question drawn in dust, asking why this object resists the usual rules, while still drifting so calmly through our system. From here, the story of 3 Atlas naturally turns toward theory. To make sense of a stable inward-pointing structure of that size, researchers begin to explore whether Atlas might not be a single, smooth body at all, but a coordinated collection of smaller pieces moving together. The next step is to follow that line of thought into the realm of swarms and predictive models, and see how far they can go in explaining what Hubble has shown us about 3 Atlas. Before Hubble ever opened its eyes on that strange teardrop, a few researchers had already drawn something very similar on paper. They were not imagining a simple comet. They were testing a different picture of 3 Atlas 1, in which Atlas was not a single solid chunk of ice, but a loose congregation of many small bodies moving together. In this model, 3 Atlas is a swarm. Instead of one nucleus, Atlas is treated as a cluster of micro-objects, each perhaps tens or hundreds of meters across, bound by a shallow combination of gravity and subtle electromagnetic forces. When sunlight strikes such a cluster, the particles in the outer layers of Atlas still feel radiation pressure, but their collective behavior can be more complex than a single rigid body. The team exploring this idea asked a simple question. If 3 Atlas were a swarm rather than a monolith, what geometry would naturally appear around Atlas as dust and small fragments were driven away from the cluster's heart? They built numerical experiments where Atlas was replaced by thousands of tiny points, each influenced by the Sun, the cluster, and the faint tug of radiation. When they let their simulated version of 3 Atlas evolve, a particular pattern emerged. Material near the front of the moving swarm of Atlas did not simply peel off and fall backward. Instead, a dense, narrow enhancement grew on the sunward side of the model Atlas, tapering outward along the direction toward the Sun. On the plots, this structure had the same general proportions as the teardrop later seen around real 3i Atlas. The anomaly appears when the numbers are compared. In cross-section and length, the predicted sunward feature around model Atlas matched the Hubble measurements for actual Atlas to within about 1%. For a system with so many parameters and uncertainties, that level of agreement is unusually tight. It does not prove that 3i Atlas is a swarm, but it does mean the swarm hypothesis cannot be dismissed as a casual guess. For the scientists working with these simulations, the match changes the tone of the debate. 3. Atlas now sits at the intersection of observation and a specific testable theory, rather than in a fog of vague descriptions. If Atlas behaves like a swarm, then other consequences should follow: differences in how light scatters from the coma, or in how small perturbations ripple through the structure around Atlas. Quietly, this brings a sense of anticipation. 3i Atlas becomes a puzzle that might be solvable, not just an odd shape on a distant image. The story of Atlas flows from pure surprise into a more patient phase, where rival explanations are invited in and asked to stand next to the same data. From here, attention turns to those competing models to see how far they can go in reproducing what we see around 3i Atlas, and where they begin to fall short. Not everyone is ready to accept that 3i Atlas has become a swarm in the sky. For many planetary scientists, the first instinct is to ask whether more familiar comet physics can still explain what we see around Atlas. One camp suggests that the sunward feature of 3i Atlas may be an illusion born from vigorous cryovolcanism near the nucleus. In that view, Atlas is venting gas and dust from a few powerful jets on the day side, and the apparent teardrop is just a bright plume seen almost head-on. If 3i Atlas happens to be oriented so that those vents aim partly toward Earth, the geometry could make a fan of material look like a narrow line. Another camp focuses on perspective. They argue that if the main dust tail of 3i Atlas lies mostly along our line of sight, projection effects could compress a broad structure into a thin sunward-looking streak. In this picture, Atlas is still behaving like a conventional comet, and the strange shape disappears once we mentally rotate the scene into 3 dimensions. The anomaly arises when those alternative models are checked against the details. Sustained jets on 3i Atlas must provide enough energy to hold a 60,000 km structure in a stable tapered form, yet the light from Atlas does not show the strong rotational modulation those focused plumes would produce. Viewing angle explanations for Atlas must recreate the observed symmetry and brightness profile along the feature, but they struggle to match the smooth inward-pointing gradient without invoking fine-tuned alignments. Rather than closing the case, these tensions keep the discussion around 3i Atlas alive and careful. Each hypothesis swarm cryovolcanism projection draws different maps on the same images of Atlas, and makes different promises about what further data should reveal. For observers following the debate, there is a quiet reassurance in that process. 3. Atlas becomes a shared exercise in testing ideas, not a contest to crown a quick winner. As attention turns to deeper measurements of polarization and chemistry around Atlas, the hope is that those independent clues will gently favour one family of models over the others and bring the picture of 3i Atlas into slightly sharper focus. While shapes and tails invite the eye, another clue about 3i Atlas emerges in the way its light is polarized. When astronomers pass the glow of Atlas through special filters, they can measure how the electric field of the scattered sunlight has been twisted and aligned by dust. For most comets, that polarization follows a familiar curve. At certain phase angles, the signal rises in a predictable way, and when the comet sits almost in line with the Sun and Earth, the polarization of typical nuclei tends to settle into a narrow range. 3i Atlas quietly steps away from that pattern, showing a negative polarization signature at viewing angles where ordinary comets would not. In practical terms, the grains around Atlas seem to scatter light as if they have a different texture or internal structure. The dust of 3i Atlas may be more compact, more glassy, or coated in films that have been etched by interstellar radiation for far longer than anything bound to our Sun. At the same time, spectra reveal that the gas around Atlas is rich in carbon dioxide and other volatiles in combinations that are rare in the inner solar system. Taken together, these measurements deepen the sense of otherness around 3i Atlas. It is not only the geometry of Atlas that resists easy classification, but also the microscopic behavior of the material that reflects its light. If the swarm and cryovolcanism models describe large-scale motion polarization and chemistry, around 3i Atlas describe the fine grain of its skin. The anomaly is that all these indicators point in the same direction toward dust and ices, that have been processed in harsher, longer interstellar conditions than our local comets ever experienced. 3 Atlas begins to look less like an outlier within a known family and more like a representative of a different population altogether. For observers, that realization brings a quiet shift in mood. Instead of trying to force 3I Atlas into old categories, the data invite us to treat Atlas as a sample from a wider galactic ecology of small bodies. From here, the narrative of 3 Atlas turns from structure and surface toward motion and control, asking whether the path of Atlas through our system is entirely passive, or if there are deeper patterns hidden in the way 3 Atlas changes course. For a while, the motion of 3 Atlas seemed almost comfortingly predictable. Gravity pulled Atlas along a hyperbolic path that computers could trace weeks and months ahead without much trouble. Then the navigation team at JPL began to notice that the forecasts in the sky were quietly parting ways. When they compared where 3I Atlas should be with where Atlas actually appeared on precise images, the difference was small at first. Night after night, however, that difference grew not along the line toward or away from the sun, but sideways. Soon the accumulated offset reached roughly 1.1 million kilometers in the lateral direction. On paper, 3 Atlas was running parallel to its predicted track, like a train that had slipped onto a neighboring invisible rail. Standard models, which let Atlas respond only to gravity and modest outgassing, could not keep the simulated position and the real Atlas aligned. For an ordinary comet, tiny jets of escaping gas can nudge the nucleus and create non-gravitational acceleration. Analysts tried to give 3I Atlas more freedom in those parameters, tuning the outflow to see if Atlas would drift in the right way. Each attempt to force the numbers into place demanded venting patterns and thrust asymmetries that did not match what telescopes saw around Atlas. The anomaly is not just that 3 Atlas moved, but that Atlas seemed to correct its path with a smooth, deliberate offset. The motion of Atlas lacked the irregular jitters of random outbursts, and instead resembled a gentle, continuous course adjustment. To some, that pattern still belongs to nature. To others, it looks uncomfortably like the behavior of a vehicle trimming its trajectory. Sitting with that thought changes how the story of 3 Atlas is felt, even if no conclusion is drawn. Atlas becomes less of a passive passenger on the solar system's gravity field, and more of an active participant in its own journey. The next logical step is to look for changes in energy around 3I Atlas, to see whether Atlas shows any thermal signatures that might hint at a hidden source of thrust. The search for a cause behind the course change of 3 Atlas led observers to look not only at position but at warmth. If Atlas was adjusting its path, some exchange of energy had to be taking place, and sensitive infrared instruments were already watching 3I Atlas closely. On one quiet run of data from the Very Large Telescope in Chile, a pattern emerged. For most of the night, 3 Atlas glowed with a faint, steady thermal signature expected from a cold object reflecting sunlight and slowly radiating away absorbed heat. Then, over the span of minutes, Atlas brightened in the infrared, as though a small furnace had briefly been lit somewhere on or within 3I Atlas. The pulse lasted for about 12 minutes before the thermal emission from Atlas slid calmly back down to its previous baseline. There was no corresponding flare in visible light, no violent plume erupting from 3 Atlas to explain the spike as a sudden dust outburst. Instead, the warmth rose and fell like a controlled exhale confined in time and apparently limited in scale. When teams modelled the cooling curve of 3 Atlas after the spike, the shape did not look like a hot patch of surface slowly radiating away energy in the usual way. The response from Atlas resembled in its timing and slope the kind of transient signature predicted for a magnetohydrodynamic drive, a brief period when charged plasma is accelerated along magnetic fields, converting stored energy into directed motion before shutting off. On paper, it was as if 3 Atlas had for a few minutes behaved like a testbed for propulsion concepts, usually confined to theoretical studies. The anomaly does not force a single interpretation. Localized pockets of pressurized gas inside 3I Atlas might rupture and reseal or subsurface. Phase changes in Atlas could mimic elements of the signal without involving any engineered system. Yet the match between the observed pulse and MHD-like curves is close enough to keep that comparison gently alive in discussion. For people following the story, this possibility adds a quiet layer of tension around 3 Atlas. Atlas might still be a purely natural body navigating a complex environment, or 3 Atlas might be using deeper physical processes in ways we have not yet seen up close. The next development in the narrative comes when telescopes lose sight of Atlas altogether for a short time, and the path of 3 Atlas seems to jump in a way that stretches our sense of what slow, continuous motion should look like. For a time, tracking networks around the world settled into a steady rhythm with 3 Atlas. Teams found that small variations in the light from Atlas repeated every 247 seconds, as though some feature on 3 Atlas was rotating in and out of view with clock-like regularity. Using that period as a metronome, observatories synchronized their exposures so that each new frame caught the same rotational phase of 3I Atlas. In effect, the global system of telescopes began to breathe in time, with Atlas stacking signals and sharpening their picture of the visitor's behavior. The pulse of 247 seconds became a comforting sign that 3 Atlas was still under watch and still obeying a pattern they could predict. Then, without warning, the data stream from 3 Atlas began to thin. One station lost its lock on Atlas, then another, until the scheduled exposures returned only empty starfields where 3 Atlas should have been. Within 10 minutes, every major observatory that had been tuned to 3 Atlas reported the same thing: no trace of the visitor at the expected coordinates. Normally, when a comet like Atlas slips behind the Sun or dips below a horizon, the loss of contact has a clear geometric cause. This time, the ephemerides for 3 Atlas still placed at last in open view, with no clear obstruction and no obvious instrumental failure. For approximately 47 minutes, the sky seemed to offer no sign that 3 Atlas existed at all. When adaptive searches widened their fields and recalculated likely positions, 3 Atlas reappeared. The new coordinates placed at last on a slightly different trajectory, offset in a way that could not be bridged by the distance light would travel during the blackout. In simple plots, it looked as though 3 Atlas had stepped from one point in space to another, leaving no trace of the path in between. That apparent jump is almost certainly a clue about how we are modelling 3 Atlas, not a true violation of cosmic speed limits. Yet the feeling it stirs is real. For those watching, Atlas suddenly seems less bound to smooth continuous curves and more associated with discrete, difficult-to-explain transitions. The next move in the narrative is to ask whether 3 Atlas did more than shift position during that gap, and to examine the strange data embedded in the networks that were listening, while Atlas seemed to be gone. When the blackout around 3 Atlas ended, telescopes were not the only systems that had been listening. Data centers that handle tracking information for Atlas found something unusual woven into their own traffic. During the 47 minutes when 3 Atlas was absent from the sky, a pattern of binary digits had flowed through parts of the monitoring network. At first, engineers assumed the strange packets were just noise or a side effect of systems trying and failing to lock onto Atlas. Only later, when the sequences were examined more carefully, did teams notice that the timing of the bursts was still synchronized to the 247-second rhythm of 3I Atlas. When analysts began to decode the pattern, the content was not images or normal telemetry from Atlas. Instead, the stream linked to 3I Atlas resolved into sets of numbers that resembled coordinates and timestamps. Plotted on orbital diagrams, those values traced a series of future intersections between the path of 3 Atlas and the orbit of Earth. One date in particular stood out. In the early 2030s, the projected track of 3 Atlas and our planet's path approached each other more closely than at any other time beyond the current apparition. The cryptic message associated with Atlas seemed to mark that window with extra precision, as if highlighting a rendezvous opportunity years in advance. Faced with that interpretation, the International Asteroid Warning Network quietly placed the decoded file linked to 3I Atlas under restricted access. Public bulletins about Atlas continued to describe a harmless flyby, while behind the scenes discussion grew around how best to follow 3I Atlas over the long term. Some reports suggest that a loosely coordinated effort nicknamed Helios in internal documents began to take shape as a way to maintain continuous awareness of Atlas beyond the usual campaign. For outside observers, these hints add a muted sense of intrigue to the journey of 3 Atlas. Atlas may simply be providing a natural set of waypoints where careful study will be easiest, or 3. I Atlas may be mapping our neighbourhood with a purpose we do not yet grasp. Either way, the story of Atlas now extends well past this passage into a future date when our world and the path of 3 Atlas draw near again, and the questions surrounding this visitor are likely to return with new urgency. 15 spacecraft rarely look at the same small object at the same time. For 3 Atlas, that is exactly what happened. Across the inner solar system, missions that usually chase their own targets were asked to spare time for a visitor from outside. Hubble James Webb solar observatories, planetary orbiters, Even deep space probes turned their instruments toward 3I Atlas in carefully scheduled windows. The coordination maps for Atlas looked less like a routine campaign and more like an orchestra score, with each mission assigned a specific part in watching 3I Atlas. On paper, the official reason was simple. 3I Atlas represented only the third confirmed interstellar object, and Atlas was moving too fast for any dedicated spacecraft to be launched in time. If scientists wanted a complete record of Atlas, they had to borrow every eye already in flight. The anomaly lies in the intensity of that focus. Many near-Earth asteroids pass closer than 3I Atlas and never receive more than a handful of radar tracks and optical snapshots. For Atlas, a web of dozens of instruments logged spectra, polarimetry, light curves, and positional data hour by hour, as though 3I Atlas were both a rare specimen and a test. People inside the agencies felt a subtle shift. 3I Atlas was framed publicly as a scientific opportunity, but the level of attention suggested that Atlas also touched quiet questions about planetary defense and preparedness. There was no announced threat from Atlas, no impact scenario tied to 3I Atlas, yet the machinery built to guard our planet had clearly taken notice. From here, the narrative around 3I Atlas turns toward what those instruments actually saw. Out of the dense stream of measurements on Atlas 1 pattern stands out a persistent non-gravitational push that standard models cannot fully account for, and that becomes the next focus of the story of 3I Atlas. When the navigation logs for 3I Atlas were examined in more detail, one number refused to blend into the background. In the models that tried to keep Atlas on its observed path, a persistent non-gravitational acceleration of roughly 135 km per day squared had to be added. For an object like 3I Atlas, gravity should do almost all of the work. Any extra push on Atlas is usually a small correction, attributed to jets of gas sneaking out of sunlit fissures. In most comets, those corrections are gentle, irregular, and tied closely to visible activity around the nucleus. With 3I Atlas, the correction behaves differently. The extra acceleration on Atlas points in a direction that does not line up neatly with the simple pattern of outgassing. The magnitude for 3I Atlas is also larger than expected, given the measured amount of material streaming off Atlas into space. Analysts tried to reconcile the numbers by letting 3I Atlas vent in more complex ways. They allowed uneven heating, rotating jets, and asymmetric plumes on Atlas, but every scenario that fit the dynamics created side effects that did not appear in the coma or light curve of 3I Atlas. The data kept nudging the fits back to an uncomfortable conclusion. Something more than ordinary recoil from escaping gas seems to be at work on Atlas. The anomaly does not force talk of machines or intent. 3I Atlas might possess buried reservoirs or structural quirks that channel momentum in ways we have not yet captured. Still, the smooth, sustained nature of the 135 km per day squared term makes Atlas feel less like a rock being pushed by random gusts, and more like an object under subtle, continuous guidance. For those following the story, this realization adds a quiet weight to the trajectory plots of 3I Atlas. Each update to the orbit of Atlas is no longer just a technical refinement, but a reminder that our understanding is incomplete. The next question is how the flow of information about 3I Atlas is managed, especially during the critical weeks, when that unexplained acceleration and other anomalies in Atlas became most prominent. Public silence around a scientific object is usually just a quirk of timing. With 3I Atlas, the quiet arrived at the very moment when interest in Atlas was rising fastest. At the start of October, a government shutdown in Washington halted many outward-facing functions. For 3I Atlas, that meant NASA's public affairs team, the people who translate raw data on Atlas into press releases and briefings, were temporarily furloughed. Mission operations for spacecraft tracking. Atlas continued classified as essential, but the flow of official updates about 3I Atlas slowed and then nearly stopped. Over the next 42 days, 3I Atlas passed through. Perihelion brightened and displayed the non-gravitational acceleration that modelers were struggling to explain. Telescopes kept watching Atlas in internal dashboards filled with plots and reports. Outside, however, those who had been following 3I Atlas saw only occasional notes with little detail about the most active phase of the encounter. The anomaly in this part of the story is procedural rather than physical. The same network that had mobilized 15 spacecraft for 3I Atlas now appeared muted just when the behavior of Atlas was most unusual. Some researchers treat that gap as a simple consequence of bureaucracy colliding with celestial timing. Others find it harder to dismiss. In their view, 3I Atlas exposed a vulnerability in how information is shared, where a visitor like At Last can become more mysterious to the public precisely when it becomes most interesting to science. Either way, those 42 days become a soft hinge in the narrative of 3 At Last, a period when At Last was watched more than ever yet talked about less. As operations and communications return to normal, attention shifts to how voices around 3 At Last frame what has been seen. The next part of the story explores the tension between those who see in At Last hints of artificial origin and those who urge caution against jumping into extraordinary explanations. Long before 3 At Last arrived, some scientists had argued that interstellar visitors might not all be natural. For them, the strange behaviour of At Last feels like a test case they had been expecting. Astrophysicist voices who are open to artificial origin ideas point to the orbit of 3 At Last. They note that At Last moves on a path that is both hyperbolic and unusually aligned, and that the non-gravitational acceleration of At Last does not sit comfortably inside standard comet models. In their estimates, the combined odds of such an object occurring by chance are low enough that they allow for a 30 to 40% probability that 3 At Last could be engineered. Others, watching the same data, react with concern to that line of reasoning. They see in 3 At Last a classic example of what they call a gap hypothesis, where every hole in understanding is used as an opening to insert design. If each anomaly around At Last is treated as evidence for intent, rather than a sign that physics and chemistry are incomplete, they worry that 3 At Last will become more of a canvas for imagination than a subject for measurement. The tension is not about the numbers themselves, but about standards of proof. Cautious researchers insist that for 3 At Last every conventional explanation should be exhausted before artificial scenarios are entertained. They point out that comets and small bodies have surprised us before, and that 3 At Last might simply be the latest member of a population we are only now sampling. In quiet discussions, the story of At Last becomes a mirror for the scientific method. 3 At Last forces a choice between treating anomalies as invitations to expand natural models or as hints of something constructed. Neither stance requires anger or dismissal, but both shape how new results on At Last are interpreted and shared. For those listening, this part of the narrative around 3 At Last carries a gentle warning. If we let every unexplained feature of At Last stand as proof of design, we risk closing off the hard work of finding deeper natural mechanisms. If we refuse even to consider unusual possibilities for 3 At Last, we risk blinding ourselves to signals that do not fit our expectations. Balancing those instincts becomes part of how we learn from 3 At Last, without rushing ahead of what the evidence can truly bear. By the time 3 At Last sweeps past its closest approach, the catalogues already feel slightly out of date. The words astronomers usually reach for comet asteroid icy small body sit uneasily next to the dossier of anomalies attached to At Last. On paper, 3 At Last looks simple enough. At Last follows a hyperbolic path, carries ices, grows a coma, and extended structures as it nears the sun. In practice, At Last carries an extreme carbon dioxide ratio, an unusual polarization signature, a sunward teardrop, and a sustained non-gravitational push that strain the edges of existing classes. The anomaly is not just that 3 At Last is strange. The deeper issue is that At Last shares the stage with other interstellar visitors that are also unlike one another. In less than a decade, the sample of bodies from beyond the solar system has revealed diversity that outpaces the language we use to describe them. That recognition becomes a quiet turning point. Instead of arguing about whether 3 At Last fits a known box, scientists begin to sketch new branches on the tree of small bodies where At Last might belong. Some of those branches imagine families of heavily processed natural objects like At Last. Others leave room for more exotic possibilities without assigning any particular role to 3 At Last. For people listening, this shift in focus softens the narrative around 3 At Last. At Last no longer has to resolve every question about origin in one passage through our sky. 3 At Last can instead serve as a reminder that our classifications are tools, not laws, and that the universe will keep handing us objects that bend those tools out of shape. As 3 At Last fades into the outer darkness again, the story does not end so much as widen. The next time a distant point of light appears on a hyperbolic track, the questions we ask will be shaped by what At Last has already taught us about how limited our old categories were and how much room remains to expand them. As 3 At Last drifts back into the dark, its questions stay with you soft as distant starlight. Tonight, you do not need to solve them. Just breathe Let your thoughts move as slowly as Atlas and fall asleep knowing the universe is still quietly unfolding around you, quietly holding watch.